Today we're going to be going over single replacement reactions, both how to identify them and how to predict their products. So let's start with identification. To identify a single replacement reaction, there has to be a change in oxidation numbers. So there must be a change. So there's two ways of doing it. The way I like to do it, which works most of the time, I'm calling it the easy way, is to look for reactions that have an obvious change in oxidation state. And the way we find this obvious change is we use our rules. So here are my elements, elements A, B, and C. They're obviously substitute elements. Now, when elements are alone, their oxidation state is 0. And when they're in a compound, like B and A are here, they are not 0. So A goes from 0 to not 0, and B goes from not 0 to 0. Now, I don't know what the not zeros are, but I know that they're not 0, and that counts as a change, so that's my my single replacement reaction. So that's the easy way. The hard way would be if there was a reaction that was like this, unfortunately, right, where you were like A, B plus CD, and then you had to, and then they do something with it where you have, you know, what would it be? It would be, I guess we could do C, B plus A, D. With this setup, you'd have to actually, if you got reactions like this, you'd have to do it the hard way, which is to assign the oxidation states for every compound in the problem, which, keep in mind, these tend to be multiple choice questions. So this is, you know, this is option A. And then you've got B, C, and D. And so you've got all these reactions, and you're going to have to assign all the oxidation states to every number. So it ends up being typically around 16 problems. And then find the reaction where there's a change. If there's no change in oxidation state, then it doesn't count as single replacement, or redox for that matter, specifically. And if there is a change, then that does count as a redox reaction. Single replacement are always redox because by definition, the 0, not 0 change makes them redox reactions. So those are the two ways to identify a redox reaction. Now, to actually predict the products of table J, we're going to need to use, to predict the products of a single replacement reaction, we're going to need table J. So table J is called the activity series. Now, a couple things about it. We're going to use this for this topic. We also use it for predicting batteries. It's usually our first step for batteries, but the same rules apply. Electrons always flow down table J. Higher metals replace lower metals on table J in compounds. Also, the metal side is different from the non-metal side. So in other words, even though lithium is the highest metal, F2 is the highest non-metal, they're not equally as reactive, meaning the column for metals and the column for non-metals are independent of each other, so you can't cross between the two. All right, and the last bit is that H2 can act, or hydrogen, H or H2, it doesn't matter, can act as a metal, and its position on the activity series is right here. All right, and so the higher metals are more unstable, they're more active, and the lower metals would be more stable, they're less active. Now let's go to the work. So what we do is higher metals replace lower metals in compounds, and the reason why is what I just mentioned. The higher metals are more unstable, and so they would rather be in a compound to stabilize them than the lower metals, which can handle being alone more easily. That's essentially what's going on. So we've got two metals here. We've got K, and then we've got Cr, and the question is, are they going to trade places? Meaning the metals usually swap, or we say the metal swap or non-metal swap, depending on the problem. So this is one where the metals will swap. But the issue is they will only swap if K is higher on table J than Cr. And so when we go to table J, we say, all right, K is up here, Cr is below it. So K and Cr are going to trade places. So Cr comes out, K goes in. Now, the fact that it was Cr2 here is because Cr is crisscrossed with SO4. Now that Cr is alone, it's in its elemental form. It's a single monoatomic element. The only time it would be doubled is if it were part of Brinkelhoff and it were diatomic. But that's only 7 elements, and Cr is not one of them. So now the next part is K and SO4 have to be crisscrossed as well. In other words, SO4 is -2 as a polyatomic. K is group 1, so it's +1. When I crisscross those, I get K2SO4. So now that is a completed single replacement reaction, but we're not done yet. For these reactions, the next step would be to balance it. So balancing this shouldn't be too hard. 2, 1, 2, 1. That takes care of the balancing. But then we also have to worry about, well, K went from 0 over here when it's alone to +1. So K lost 1 electron. And then CR, it's 0 when it's alone, but in this case it's +1. And the reason being is because SO4 as a polyatomic is -2. I'm not going to write it in, it'll get too busy, but CR gained an electron. So now the next step would be you could write half reactions for these. I'm not going to do that here. We should already know how to do half reactions. I'm just going to do the rest of the problems predicting the product. So I'm going to shorten this up a little bit. So let's go to the next one. Aluminum and chromium. They'll trade places. That's single replacement. Now, they only trade places if aluminum is above chromium. Okay? Al is above Cr. So Al is more unstable. So it's better to put Al, it's better to have Al in the compound than Cr, because Cr is more stable on its own than Al is. So now we get Al is going to be with SO4. We have to crisscross these. SO4 as a polyatomic is -2, Al plus 3. So when I crisscross them, my formula is Al2, SO4, 3 times. I need the parentheses on that problem. So that's my single replacement reaction. If I were going to do my half reactions, well, my oxidation states would be 0, +1, 0, +3. And so those are the ones that matter for oxidation states. The reason I know this is +1, again, is because I'm uncrisscrossing. I know SO4 is -2. So the only way I get this is by uncrisscrossing, or you could use your rules and assign oxidation states. This is 0, that's got to be therefore +1. So there's a number of ways you can figure out CRs, and you should be able to do that. Let's do the next one. Will Fe replace Cr? Well, only if Fe is above Cr, and if you look, Fe is below. So what this means is that the more stable element is out of the compound already. So if you mix these two chemicals, nothing happens, because they are in the better configuration. Basically, what single replacement reactions, what drives them is essentially these two metals in this configuration are more unstable than if they swapped and were in this configuration. And the reason is because K is a more unstable element than Cr when they're in their elemental form. So it's better to have the more unstable thing be in the compound, because being in the compound makes you satisfy the octet rule, which makes you stable. And so therefore, this is preferred, this is more stable as a combination, meaning these two things on the right, than these two on the left. And the same goes for number 2 for the same exact reason. The reason this reaction doesn't happen is because we're in the more stable configuration of these metals anyway, and they won't naturally come out. Now, that doesn't mean you can't force this reaction to go backwards. If you remember learning electrolysis, that's what electrolysis in an electrolytic cell, that's what electrolytic cells are for. They can actually force this reaction to happen, but it doesn't happen naturally. You have to put in energy to make these reactions reverse. So the next one, F2. Now, F2 is not going to trade with H. That's a common mistake. It can only trade with Cl. And the reason is F and Cl are in the same column, whereas H is in a different column, and that doesn't count. You can't cross between these. So F could swap with Cl, Br, or I. So in this case, since F is above Cl, they trade places, and you get Cl2 and HF. Now, notice this Cl did double, whereas it wasn't doubled here. And the reason is because when Cl is alone in its elemental form, it is part of Brinkelhoff, it gets doubled, just the same reason that F2 got doubled. Okay, and those are its oxidation states when they're in the elemental form. And then when they're in a compound, F's going to be -1, +1 crisscross, and then this one's already done for us, but -1 and +1 in the reverse order. And so those are the oxidation states. And then the last one, Br, can Br trade with Cl? Well, it's real simple. Since Cl's already above Br, then that means no reaction is going to happen, because again, chlorine is more unstable, and so it's in the compound which stabilizes it. So it's better to have bromine be not in the compound than it is chlorine, because bromine is more stable on its own than chlorine. That's what table J tells us.